Remember valence bond theory? Chem 1A? Hopefully you remember hearing about it at least. You might want to brush up on it because it's going to show up on the final exam. So valence bond theory is where we looked at the number of electron groups and we hybridized orbitals to get equivalent orbitals. And so we saw that if we had two electron groups, they would get away from each other, just like two balloons tied together would be opposite of each other. And so you start with the s, and then you move through the three p orbitals and into the d orbitals. So if you need two orbitals hybridized, you're going to have an s and a p. If you need four are going to make a tetrahedron, and the hybridization then is sp3 because you need a total of 4 orbitals. A square planar is going to be sp2d, and that's different than what we talked about in 1a, so don't worry about that one. Octahedral, we need to have 6. So to get 6, we've got the s and 3 p orbitals and 2 d orbitals. So we can explain or describe bonding using valence bond theory. The coordinate covalent bond is an overlap between a filled atomic orbital on the ligand and an empty atomic orbital on the metal. Okay, so the empty orbitals on the metal ion. The metal ion orbitals are hybridized according to the geometry of the complex ion. So again, just like we determined the hybridization of compounds or of a central atom by looking at how many electron groups are there, looking at the geometry told us what the hybridization is, that's what we're going to do here as well. So the valence bond theory does explain the geometry, but it does not explain other things that are observed, such as different colors and different types of magnetism. Some of these compounds are magnetic and some of them are not. So complex ions form because of attractions between the electrons on the ligands and the positive charge on the metal ion. But ligand electrons will also repel metal electrons that are in unhybridized d orbitals. So in an octahedral complex ion, those ligands are going to overlap with 2 of the unhybridized d orbitals, and then the other 3 are going to fall between the ligands. So we need a picture for this. So what we've got here, these little negative charges here, those are the ligands, right? And they're in an octahedral shape. And then what we're seeing in the middle, in the light green, those are unhybridized d orbitals. And so 4 of them are like a cloverleaf shape, just oriented differently in space. And the 5th one is weird. It's like a dumbbell with a life preserver around the middle or something. So in this arrangement, the ligands overlap with this unhybridized orbital. They collide with each other. And so there is repulsion. They don't like being in each other's space. They repel each other. And so that's going to be a higher energy. So this one's a higher energy. And this one's also a higher energy because the ligands overlap with those unhybridized orbitals. So that's not good. It's high energy. So that's these 2 guys up here. Here, the unhybridized orbitals with the other orientations can fit between the ligands, and so they don't run directly into each other. You see that? So these are going to be lower in energy. These 3 are going to be lower in energy, and these 3 are going to be higher in energy. So instead of having 5 d orbitals that are all the same energy on that central atom, we're going to have 2 that are higher and 3 that are lower. And both of these are a little bit higher than the free atom, but these are only a tiny bit higher and these are significantly higher. This difference between the low and the high energy ones is the delta, that's the crystal field. That's the splitting energy. So that crystal field splitting energy, the difference in energy between the split d orbitals, and how big that difference is depends on the ligand and the metal ion. So we can talk about a strong field complex where the splitting is large. The difference in energy is big. Or we can talk about a weak field complex where the splitting is small. There's just a little difference between those sets of orbitals. So crystal field strength explains different colors of complex ions. So in our lab practical, we had some complex ions that were used as tests for some of the transition metals, and we saw things like this that were brightly colored solutions. The color of a solution depends on what energies of light are being absorbed by the solution and what are being transmitted by the solution. So if you had something that was black, like my shirt today, it absorbs all wavelengths, it doesn't reflect anything. Something that's white, like a piece of paper, doesn't absorb light, it just reflects everything. So I think we all know from experience that if you go out in the sun in August in Fresno, California, and you're wearing all black, black shirt, black pants, black hat, you're going to be a lot hotter than if you were wearing all white, right? Because white reflects a lot of that energy from the sun, whereas black absorbs it. So when we see a color, like the red here, that solution is absorbing some of the visible light, but transmitting the color that we see. So it's transmitting the red, and it's absorbing most of the other colors. And so it's absorbing the complementary colors. So here we have this hexa aqua titanium 3 complex ion solution, and it's purple. So it's reflecting purple and absorbing on the other side of the color wheel. These are complementary colors, purple and yellow. And here we can look at the absorbance as we look at different frequencies, different wavelengths of light, and we see that it's really not absorbing here in the purple at all, but as we go towards the green and the yellow and a little bit into the orange, there's significant absorbance, and then it drops off again. So because it's absorbing the wavelengths over here, transmitting these, what our eyes perceive is a purple solution. And that light that is absorbed and reflected is due to the transitions from the low energy d orbitals to the higher energy ones. And the difference here is on the order of visible light, and so that's why these are colored. So we can actually calculate the crystal field splitting by looking at the color or the wavelengths that are absorbed or transmitted. So the energy of a photon is Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. And that is equal to the crystal field splitting energy. So we're looking at the energy that's absorbed, and we can calculate delta. So the complex ion CO and H3 NO2 2+ is yellow. Estimate the crystal field splitting energy in kilojoules per mole for this ion. So the tricky thing about this is we're not going to use the frequency of yellow light because that's being transmitted. That's not being absorbed. We want to look at the complementary color. So if we're seeing yellow, that means it's absorbing purple. And it says estimate. They didn't give us a specific wavelength. They're just saying it looks yellow. Okay, so we just need to pick something over here. Let's pick halfway between 400 and 430 nanometers. So we'll say it's absorbing around the 415 nanometers. So the wavelength that it's absorbing is 415 nanometers. Now the equation is hc over lambda. H is Planck's constant. No, I think it's 2. And C, oops, I forgot the units. Joule seconds. I don't expect you to memorize that number. I only remember it on good days. Speed of light, 3 times 10 to the 8th meters per second. Again, I don't expect you to memorize that. And then we're going to divide by the wavelength that was absorbed. 415 nanometers. Before we get out the calculator, we want to check our units. So the seconds are going to cancel. We're looking for joules, kilojoules, so we don't want the joule to cancel out, but we don't want nanometers and meters in here. These aren't going to cancel. We need to convert nanometers into meters. You can do that separately, or you can say, well, I know what nano stands for. So I'm going to replace nano with what it means. So nano means times 10 to the minus 9. This is not proper scientific notation. You end up with a number like that as an answer. You need to put it in correct scientific notation. But you can use this in your calculator because your calculator doesn't care. Right? So it's just a very fast way to do unit conversions. So now the meters cancel out and we can do the math. .662, and again, I'm iffy on that too. It could be a 3. It's not really going to matter. So I'm getting 4.82 times 10 to the minus 19 joules. Did I do my math right? If you type that into the homework program as your answer, it's going to say, wrong. Isn't it nice it doesn't actually make the sound? That would really be discouraging. Buzzer. Well, what units are we supposed to have? Kilojoules per mole. Well, we could turn this into kilojoules pretty easily, right? If I want kilojoules up here, I'm going to divide by joules, so those cancel out. And then kilo stands for 10 times 10 to the 3 times 10 to the 3. So 1 kilo is 1 times 10 to the 3. So this is going to give me 4.82 times 10 to the minus 16. No. Minus, this is why you shouldn't do math in your head. Minus 22 kilojoules. That's also not the right answer. It wants energy in kilojoules per mole. How many photons is this equivalent to? It's 1 photon, right? So one of these complex ions absorbing light would be this much energy. So how much for a mole of ions? So we've got 4.82 times 10 to the minus 22 kilojoules per ion. We're going to need Avogadro's number. There's 6.022 times 10 to the 23rd ions in 1 mole of ions. I think it actually was, this was supposed to be a 3. That's okay. I think the answer is actually 288. Any questions? So, we got this equation we can use, but then if it's asking for something like kilojoules per mole, you need to be able to think about, well, how do I make that into kilojoules, which that should be pretty easy, but how do I get that to be moles? We have to have an understanding of what we're calculating. Just make sure we didn't miss anything. Okay, so we said that the ligands affect the magnitude of the crystal field splitting. So this is called the spectrochemical series, and it lists the ligands in order of their ability to split the orbitals. So cyanide typically splits them more strongly, and iodide splits them very weakly. So this is going to give us a small delta. These guys are going to give us a large delta. We're not going to worry about why. They've just observed this, and we're going to go with it. We don't even have to memorize it because it's not going to be on an in-class exam. So if you need to know whether you've got a large field or a small field, you're going to look at what your ligand is and see where it is on this in this series. Now, the metal ion also has an effect. If it has a higher charge, it's going to pull the ligands in closer, and that's going to cause bigger splitting because it causes greater repulsion. So magnetic properties can also be explained by this. So remember Hund's rule. Hund's rule says that electrons occupy degenerate orbitals singly when possible. So I'm not so big on whether you remember that this was called Hund's rule, or if I say Hund's rule, you know exactly what I'm talking about. But understanding how electrons fill orbitals is important. So in the quantum hotel analogy for electron configurations, we talk about the electrons coming in to a hotel room, that's the sublevel, and there are beds for them to choose from, right? So you've got 2 electrons coming into a room with 3 beds. Think about high school guys on some sort of field trip or something, and they're staying in this room and there's 3 beds. Are these 2 high school guys going to sleep in the same bed together? No, absolutely not, right? They're going to take their own bed. Pretty much anybody's going to do that, right? You get on a bus, right, and usually there's 2 seats together up along each side. Are you going to sit next to a stranger when there's some empty seats? No, you're going to go sit by yourself if you can. Once all those are full, then it's more socially acceptable to sit right next to a stranger. Right? So that's Hund's rule. They're going to take their own space, their own orbital, if they can. So when these d orbitals are split, the lower energy orbitals are going to fill first because it's lower in energy, right? When you fill the lower energy orbitals half full, the next electron coming in has a choice. They can either pair up with someone in the lower energy orbital, or they can go to a higher energy orbital. And which one they choose depends on that crystal field splitting. How much higher is the energy? If it's just a little bit higher, like, oh yeah, is this worth a little bit of extra money, extra energy to go have my own space, right? If it's a lot more, they're going to like, nah, I'll share and save the money, okay? So just like when we were filling orbitals in Chem 1A. So here, iron, FeCN6, 4 minus, is known to be diamagnetic. Remember those words? Diamagnetic and paramagnetic. Diamagnetic means all the electrons are paired up. Paramagnetic contains unpaired electrons. I always found this confusing because para sounds like pair, right? P-A-I-R. But it's not spelled the same. It doesn't mean the same thing. Di means two. So I think about Noah's Ark, where all the animals went into the ark 2 by 2, right? So diamagnetic, 2 by 2, everything's paired up. Paramagnetic is the other one. So here, all the electrons are paired up. This iron has 6 electrons in these orbitals. And as they come in and take their spaces, the first one's going to take this one, and then this one, and then this one. The next electron has to choose. Am I going to share with this guy, or this is a big energy difference, pay a lot of extra money to get my own space? It's not worth a lot of money. So he's going to pair up. And the next one's going to make the same decision, and the third one's going to make the same decision. And the result is that they are all paired. When all the electrons are paired up, then this ion is not going to interact with the magnetic field because it's the unpaired spinning electrons that interact with the magnetic field. So this happens because cyanide is a strong field ligand. It causes big splitting here. If we look at a different iron complex ion, this is also iron 2 with 6 electrons, but we have water, which is a weak field ligand. Now the difference in energy here is small. So the electrons come in, and the first one takes his own bed or orbital, and the next one, and the next one, and the fourth one has a choice. I can pair up with this guy or invest a little bit of extra energy and go up there. It's worth a little bit of energy to go up there and have my own space. So he does that, and then the next one's also going to go up there. The last guy coming in can still choose, but he's choosing between paired up with low energy or paired up with higher energy. So he's just going to stick down here. So the result here is that we have 4 unpaired electrons. This ion is going to interact with a magnetic field. This one is not. And crystal field splitting theory explains why that is. Any questions? So in general, complexes that have strong field ligands have fewer unpaired electrons. So when we look at this, this is a large difference. This is a strong field ligand. So we have fewer unpaired electrons. When it's a weak field ligand, and this difference is small, we have more unpaired electrons. So fewer unpaired electrons is called a low spin. More unpaired electrons is called high spin. We can only have high and low spin possibilities if we have 4 or more electrons. If you have 1, 2, or 3, they're all just going to be unpaired in the lower energy ones, and there's no options. But if you have 4, 5, 6, or 7 electrons, then you can have different possibilities. Okay. How many unpaired electrons are there in the complex ion FeCl6 3 minus? We need to know how many electrons that central metal ion has. So we need to look at the electron configuration for that metal. It's an ion, but what we want to do is we want to look at the atom first. So just iron, let's write the electron configuration. So iron is in row 4, so we go up to row 3. That's argon. So we're going to start with the electron configuration of argon, and then we're going to read the periodic table to fill in. So 4s, 2, and then 3d, and we count 1, 2, 3, 4, 5, 6. So that's the electron configuration for an iron atom. What's the charge on this iron ion? It's going to be 3 plus. So overall we have -3. We have 6 chlorides. They're each -1. So the iron must be +3. So we need to remove 3 electrons from the iron. Which ones go first? The 4s go first. So we're going to get rid of all of those, and then we're going to take one of these guys. So now we just have 3d5. So we have 5 electrons. So next we're going to look at the split d orbitals. And we're going to look at the ligand and identify, is this a weak field or strong field ligand? We're just going to go back and look at the series, because I don't remember those either. So this is on the weak field end. That means a small difference in energy. So this difference is small. Now we're ready to put electrons in. We have 5 electrons. 1, 2, 3. The 4th one has to choose. Is it going to go up or stay down? Up. It's going to go up because this is just a small amount of energy. It's like, if you're in this hotel and you could spend like $2 extra a night and have your own bed, would you do it? Heck yeah. What if it was $50 a night? Yeah, maybe I'll share with a stranger, right? It's not necessarily worth it. And then the next one will also go up there. So there's our 5 electrons. How many unpaired electrons are there? 5. Let's do COCN6 4 minus. Again, we have to start with the electron configuration for cobalt, which is argon, 4s2, and then we count across. This has 1 more electron than iron, so it's going to be 3d7. And then cyanide is -1 times 6 is -4. And then we have this. So this is a +2 ion. So then looking at the cobalt-2 ion, we lose those 4s electrons first. And there's our 2 electrons. We don't need to lose anything else. 3d7. So this one has 7 electrons that we have to put into these orbitals. Again, we need to know, is this difference large or small? So we go back and look, oh, it's going to be big. Cyanide's the biggest one. So delta is large. And then we take our 7 electrons and we stick them in here. 1, 2, 3. And this is a situation where you have to pay $50 a night to have your own bed, on top of what you're already paying. So this one's like, nah, I'm going to share. So there's 4, 5, 6, and then number 7 has no choice but to go up there. How many unpaired electrons? 1. So there could be a question like that on the take-home exam. Any questions? So those are octahedral complexes. In tetrahedral and square planar complexes, the orbital splitting is different. In tetrahedral complexes, the splitting is opposite. We have 3 that are high and 2 that are low. And here, these are typically going to be high spin, which is what we get when delta is smaller. In square planar, it's more complicated. And it actually splits into 4 different levels. 2 at the bottom, and then 3 individually increasing in height. So these are almost always low spin, so they're gonna fill up and pair up as they go along.